transmitted field amplitudes, and that is called as the reflection coefficient and the transmission coefficient. And we also looked at how it is going to happen when our one medium is a perfect conductor. So we saw that you will have a complete reflection, and the transmission and reflection both, they will superimpose to form a standing wave pattern. And this is what we have seen here. See this one. You will see a standing wave pattern where you will get maximas and minimas. And I also showed it to you with the help of some videos, how the electromagnetic wave looks like. Okay, so today we have an example of this normal incidence. So if you can see, let's very quickly go through this example because it is very straightforward. So it is saying that it has a boundary at x is equal to 0. So your x is equal to 0 is the boundary. And this is my medium 1, and this is my medium 2. And my medium 1 has this characteristics. That is, the dielectric constant is 9, mu r1 is 1, and sigma 1 is 0. And mu r2 is 4, epsilon r2 is 4, mu r2 is 1, and sigma 2 is 0. And now what it is saying, that 100 megahertz wave is in medium 1, and it is normally incident on the boundary. And its incident field in phasor form is given by this one. So now you need to find all these things: the reflection coefficient, transmission coefficient, beta 1, beta 2, the total, the reflected field, transmitted field, the total, the incident field, the reflected field. This is in the instantaneous forms, and the total field in region 1 and the total field in region 2 in the instantaneous form, and also the total magnetic field in region 1. So how we are going to start here? As we know, the reflection coefficient and the transmission coefficient is depending on eta, right? Eta. So you can have eta 1 for medium 1 and eta 2 for medium 2. So eta 1 is eta naught root of, remember, mu r1 over epsilon r1. So mu r1 over epsilon r1, which is 377 by 3. Eta 2 is 377 root of mu r2 over epsilon r2. That's why you have root of 4. And therefore, you have the reflection coefficient as 0.2. And the transmission coefficient, I can calculate it as 1 plus uppercase gamma, which is the reflection coefficient, which is 1.2. And now the second part is we need to find beta 1 and beta 2, because if you see here, beta 1s are not given to us. So how can I find beta 1 and beta 2? You can first find u1, the phase velocity. From the phase velocity, you can find beta, right? So u1 is equal to c over root of mu r1 epsilon r1. This is my phase velocity, right? So c is known to me, mu r1 epsilon r1 is known to me. So the right hand side is known to me is u1, which is also equal to omega over beta 1. And omega is known to me, which is 100 megahertz is the frequency. So omega will be 2 pi times 100 megahertz. So when you put all of this, you will get beta as 2 pi radians per meter. Okay, and then you can do the same thing for your medium 2, because in medium 2, you are going to have these changes here, because it will be root of mu r2 epsilon r2. So you also got beta 2, which is 4 pi over 3 radians per meter. Now, what is the reflected field in the phasor form, reflected electric field in the phasor form? As you can see, our incident electric field, see here, incident electric field is moving in the positive x direction, and it has a component along the AY direction. So here, our reflected field will be equal to AY. This is the reflection coefficient, which is 0.2, times the incident field amplitude, which is 20, e power plus j beta 1 x, plus j, because it is the reflected field. So it is traveling in the minus x direction. So that's why it is plus j Beta 1, which we already calculated, which is 2 pi x, which is equal to AY 4 e power j 2 pi x. This is the reflected field. The transmitted field, ETS, is AY transmission coefficient, which is 1.2 times 20 e power minus j beta 2. So beta 2 is what? 4 pi over 3 times x, which is equal to AY 24 e power minus j 4 pi over 3x. So we got the reflected electric field in the phasor form. We got the transmitted electric field in the phasor form. Now we want to put it in the instantaneous form. So instantaneous form of the incident field is what? You took the phasor, take the phasor field multiplied by e power j omega t and take the real part of that, which will be this one. AY 20 cos 2 pi 10 to the power of 8t minus 2 pi x. Okay, because if remember, this is our incident field. AY 20 e power minus j beta x. AY 20 e power minus j beta 1. Beta 1 is what? 2 pi x. And then what did I say? Multiplied by e power j omega. Omega is what? 2 pi f. So 2 pi, and what is the frequency? Is 100 mega, right? Which is 10 to the power of 8 t. Multiply and then take the real part. So which will be equal to this one. AY 20 cos 2 pi 10 to the power of 8t minus 2 pi x. So similarly, you can get the reflected field because you have the reflected field in phasor form. And then what will be the total field? So the total field will be in medium 1 because it is incident field plus reflected field, which is this incident field plus the reflected. And the total and the field in the region 2 E2 in the instantaneous form, we know this one. See, it is e to the power of, sorry, AY 24 e power minus j 4 pi over 3x. So in instantaneous form, it will be AY 24 cos 2 pi 10 to the power of 8t minus 4 pi over 3 times x. And then you can also get the magnetic field in region 1, which is nothing but, what is this? This is the reflected. This is the incident magnetic field, and this is the reflected magnetic. Okay, so how I am getting this? I know my incident electric field, right? So how can I get the incident magnetic field? Yes, Hassan, can you tell me? Hassan al-Musallam, can you tell me? If I know the incident electric field, how can I get the incident magnetic field?
I'm not sure.
Hassan, come on. We are at the end. I think now you should pay attention and you should start, working for your final exam. What is the relationship between the electric field and the magnetic field, right?
Intrinsic impedance.
Yes, the intrinsic impedance. EY is equal to HI over eta 1. This is the relationship, eta 1. Eta 1, because this is in medium 1. That's why eta 1.
The magnitude, doctor.
No, the
Yes,
opposite.
I'm sorry. Yeah, I'm correcting. It's the magnitude.
And yes, he's right. It's the opposite, I think.
H equals E over.
Oh, just a second. I should write, let me write it in this manner. It is much easier for everyone. Eta 1 is equal to EI0 over HI0. Okay, so the incident field amplitude over the incident field amplitude of the electric field over incident field amplitude of the magnetic field. Okay, so let's write it in this way. Yes, of course, you can write it in the magnitude, which is EI magnitude over HI magnitude. Okay, so this is the relationship. So you have to use that. And guys, please, start, say, practicing problems, because we know it very well that our exam is the very next day of the class, of the end of the class. Okay, so similarly, you can get it for the reflected field. So you take the reflected electric field, and from the reflected electric field, you can get the reflected electric field amplitude, and then you can find the reflected magnetic field amplitude. So reflected magnetic field amplitude and the reflected electric field amplitude relation again is from the eta. So here again, it will be eta 1 is equal to the reflected field amplitude over the reflected magnetic field amplitude. Reflected electric field amplitude over the reflected magnetic field. Okay. So this was a simple example for the normal incidence, and I would encourage you to please go and look at the textbook. There are some examples done, and also in the homeworks. Okay, so now let's move on to our next type of incidence. The next type of incidence is called as Hassan. I hope now you understood, right?
Yes.
The relation between them, their amplitudes, is with respect to the in our characteristic impedance or the intrinsic impedance. Okay, so as when we started our reflection and transmission, as I told you, first we were looking at the normal incidence, and second we will look at the oblique incidence. So therefore now we are going to the oblique incidence. Now, to understand the oblique incidence, we will first try to see how we can represent the propagation constant for an electromagnetic wave which is traveling in an arbitrary direction, right? Because in normal incidence, as you can see here, in the normal incidence, our wave was not traveling in the arbitrary direction. It was traveling either in our x direction, or y direction, or z direction. So it was not traveling in the arbitrary direction. So therefore, for x, you can have beta 1, for y, and for z, you can represent it with the phase constants, beta. But here, now it is in the beta or gamma, if it is a lossy case. But remember, for our transmission and reflection examples and the derivations that we did, we assumed a lossless case. That's why our sigma is 0. Now, in an arbitrary direction, how do we represent the propagation constant in the arbitrary direction? So it can be represented with the following argument. So what we do is we first define a position vector r bar. And this r bar in the 3 dimension in our Cartesian coordinates is xax plus yay plus zaz. This is our position vector. And now we also define another vector which is called as vector k. And this vector k is this one, kxax plus kyay plus kzaz. So now what is this vector k? This vector k is including the propagation constants which are in the x direction, y direction, and z direction. And now guys, here we have dropped using beta. Now we are using k. And why we usually use k? Because in arbitrary direction, we always try to represent it in K form. So this is the typical notation that we use, K. So whenever you see K, that means, you can think that my electromagnetic wave is now traveling in the arbitrary direction. That's why we are using it as K. Okay. So now, how is the argument? The argument is in this way. See, this is my electric field, which is traveling in an arbitrary direction, and this direction is S. S. So it is E naught. E is E bar is E naught bar e power minus j k s. So I'm just considering this part. Okay. Now, what I am doing, what is this K and S? So K and S, I am now just, just give me a minute. I will explain everything to you. So now what is first? Let us see what is S. S, this S. S is nothing but I am writing S as this one. So S is this direction. And if I assume that my unit vector along this arbitrary direction S is AS, arbitrary direction S is AS, then what I'm doing, I'm finding this S, this S as the projection of my position vector along this direction S. And what is the projection of the position vector along this direction S? This will be nothing but R bar dot product with AS. This will give me what it will give me? It will give me the projection of my R bar along the S direction. And this is nothing but this S, that I'm replacing it with this one. And now if I just rearrange this, I'm seeing that it is e power minus jki, because dot product, I can interchange them. So I'm writing K times AS bar dot R bar. And this K times AS bar is nothing but my K bar, which I have defined here. And what is my AS bar? Is nothing but the unit vector along the direction of S. Got it? See? So K times AS bar is nothing but the component of my K along AX plus component of K along AY plus component of K along AZ. And that forms my vector K. And the magnitude of this vector K is root of Kx square plus Ky square plus Kz square. And now if you see, rather than showing it in this manner, which is a scalar one, see here, it's a scalar. This one, see, this is a scalar. Can you see this one? This is a scalar, Ks. Because till now, we were only looking along X direction, Y direction, and Z direction, right? So therefore, we were just saying that beta 1 Z or beta 2 Y. So we were using scalar. But now, when we are going in an arbitrary direction, it will no longer be scalar, because it will have its part along, because if you want to decompose that propagation constant again, then it will have its part along the X direction, it will have its part along the Y direction, and it will have its part along the Z direction. And that's why now you are representing it in the form of a vector, K bar dot R bar. And if you want to, just take the dot product of this, then it will be written as this. See, it will be written as this. See here, this one and this one. So if you see here, so if you dot product K and R, if you dot product this K vector with this position vector R, then you will get KXX, KYY, KZZ. So KXX, KYY, KZZ. So what does it say? It is saying that Kx is nothing but the component of my propagation constant along the x direction. Component of my propagation constant along the y direction. And the component of my propagation constant along the z direction. This is how we represent an electric field in an arbitrary direction. So we came up with first our argument. Just I'm quickly reviewing. Our argument is we first we defined our position vector, and then we define our propagation propagation constant not as a scalar but as a vector, which is this one. And then what we did is we tried to get this Ks, and when we simplified it, we end up saying that this Ks is nothing but my K bar dot with R bar. And when I dot product them, I am getting the end answer. So this is my end answer, where Kx is component of K along X direction, Ky component of K along Y direction, Kz component of K along Z direction. So I am now trying to name the components of the propagation constant along X, Y, and Z direction. And therefore, when we try to show the components, we don't use beta, we use K. Okay, we use K. So this is the notation that our book is following. So that's why we will also follow the same thing. And now, if we want to write it in the, because this is in the phasor form, if you want to write it in the instantaneous form, then it will be E naught bar cos of omega t minus kxx minus kyy and minus kz. So the component of the propagation constant along the x direction, component of the propagation constant along the y direction, and component of the propagation constant along the z direction. Okay, and remember one very important thing. This is the propagation constant. It is the k vector, right? And this k vector is along this direction. It's an arbitrary direction, right? So my k dot r, is representing this direction. And my electric field, so this is the direction. So therefore my electric field components. So my electric field components, my E naught bar, my electric field components, it can have x, only x component, or it can have only y component, or it can have x plus y component. We don't know. But till now, for our simplification, we always used only one component of electric field. So remember, that component of electric field will always be perpendicular to this direction k. So it will always be perpendicular to this direction k bar. This is what I'm saying. Okay, so with this argument where we decomposed our propagation constant into its component along x, y, z direction. So this is the generalized expression of the propagation constant. And now our special case. Suppose if we have the wave propagating is only in the x direction, then what will happen? My E bar, which is E naught, it will become e power minus j. It will be, what will be this part? It will become e power minus j kx x, only this one, because it doesn't have any component in the y direction and it doesn't have any component in the z direction. They are all turning to 0. And therefore, the total propagation constant, which was k, has only kx component. And that's why I'm, instead of writing kxx, I'm writing just k times x. Now, in this scenario, where my propagation of the wave is only in the x direction, I do not need to use this k. I do not need to use this k. I can simply replace k with beta. Okay, I can simply replace k with beta. So this is kx is nothing but this will be beta, this one. So summary, if your propagation constant is only in x direction or only in y direction or only in z direction, which is the case of normal incidence, we represent beta as our phase constant, or in a lossy case, it is gamma as our propagation constant. Okay. Now, if we are in the arbitrary direction, arbitrary direction, then we use k as our propagation constant. I would say k bar as our propagation constant, because my k bar is made up of the component of my propagation constant along the x direction, component along the y, and component along the z. Okay, so is it clear? Because guys, this is the small part where, student gets confused, because in the book, what the problems or the book does it is, from beta, from k, it will quickly change to beta. So remember, k can be changed to beta when your electromagnetic wave is no longer traveling in the arbitrary direction. This is what I wanted to emphasize. Okay, so now let's look at our incidence. So if you see here, this is our oblique incidence. So our oblique incidence is divided into two types of incidence. First is called as the perpendicular incidence, and the second is called as the parallel incidence. So now, what are the definition of the perpendicular incidence and parallel incidence? The definition is with respect to what we call it as a plane of incidence. Now, what is this plane of incidence? It is nothing but it's the plane which contains all the three directions, which is incident, reflected, and transmitted. All the three directions. That is called as the plane of incidence. So in this case, this is my incidence, right? This is my reflected, and this is my transmitted. So in which plane do we have all these three directions? Yes, Ramzi, can you tell me in which plane do we have all these three directions?
An XZ plane.
In the XZ plane, right? Which is nothing but our screen, because all these three directions are residing in our this plane, which is our XZ plane. So XZ plane is called as the plane of incidence for this case. And here also, XZ is called as the plane of incidence in our case, because this is our incident, this is our reflected, and this is our transmitted. Now, with respect to the plane of incidence, which is our XZ plane, we define what is called as perpendicular incidence, and we define what is called as parallel incidence. So what is perpendicular incidence? when my electric field is perpendicular to the plane of incidence. That is, my electric field must be perpendicular to the xz plane. Then it is called as the perpendicular incidence. And when my electric field is parallel to the plane of incidence, then it is called as the parallel incidence. So if electric field perpendicular to the plane of incidence, then we say it as perpendicular incidence. When the electric field is parallel to the plane of incidence, we say it as a parallel incidence. So the definition of perpendicular incidence and parallel incidence is only with respect to the electric field. So if electric field is becoming perpendicular to the plane of incidence, then it is called as perpendicular incidence. So that's why if you see here, this is my plane of incidence, which is XZ plane. Now, if you see, my electric fields are all coming out of the screen. Can you see this? All my electric fields are coming out of the screen. So that means my electric field is perpendicular to the XZ plane. And that's why it is called as a perpendicular incidence. And parallel incidence, if you see here, this is my electric field. And if you see here, my electric field is residing in the XZ plane. Because this is my electric field. That means if I decompose it, I will get Z component and I will get X component. So this is EX, this is EZ. I'm getting EX component and EZ component. And both these components are parallel to this XZ plane because they are now residing on the XZ plane. And that's why it is called as a parallel incidence. Clear? Yes, any questions on this one? Now, why we have only two types of incidence, perpendicular incidence and parallel incidence? Or why we divided into two types of incidence, perpendicular incidence or parallel incidence? Very straightforward to answer. Can anybody think of it? Why we have only this perpendicular and the parallel incidence? Because guys, my electric field can have X, Y, and Z component, right? It can have X, Y, and Z component. So in this particular case, when I apply the incidence to my electric field, the Y component will be treated as perpendicular incidence. And my XZ components will be treated as parallel incidence. So in summary, any field which has three components, if I find the tangential components and normal components to the plane of incidence, then they will go into these two categories. So the tangential components will go into the category of parallel incidence, and the normal components to the plane of incidence will go into the perpendicular incidence. And then you can use those expressions that we derive and you can apply it and you can find the reflected field amplitude for that particular component, this particular component. And then you can find the reflected field amplitudes for this particular components. Correct? Clear? So I'm now trying to give you a more general view because here you have one component and here you have two components. So in this case, if this is my EY, so my EY, we will use the perpendicular incidence expressions to find its reflected field amplitude and the transmitted field amplitude. And then here, if I have EX and EZ also, Then EX and EZ, I will use the formulas for the parallel incidence, and then I will find its reflected field amplitude and the transmitted field. If my electric field has all the three components, X, Y, and Z. Okay, so this is called as the oblique incidence. So what I'm going to do is we are going to take the perpendicular incidence and we will solve it carefully. We will spend enough time to understand that. And then parallel incidence is very similar to the perpendicular incidence. So there I will just show you the answers. Okay, so let's start here. So this is my oblique incidence. So you have the electromagnetic wave, which is made up of the electric field. So this is my electric field, red color coming out of the screen. This is my electric field, red color coming out of the screen. So that's why it is normal to the plane of incidence, because my plane of incidence is the XZ plane. And then this is my associated magnetic field, incident, reflected, transmitted. And what is my direction of propagations? The green one. This is my direction of propagation. So let me use a dark color. So this is my direction of propagation of the incident field. And that's why it is making, so which is my interface? The Z is equal to 0 is my interface. Okay, or I would say my XY plane is my boundary. And this is normal to the boundary. So therefore, it is making an angle of theta I, incident angle. And then this is the direction along which my reflected field is traveling. And this is the direction along which my transmitted field is traveling. And my transmitted field is making an angle of theta T. And my reflected field is also making an angle, which is theta R. Okay, so this is our problem statement. Now, first thing, we need to find the incident field. So if you see here, the incident field, okay, what is this red one? It is AY. So it has only AY component. My electric field has only AY component. And this is the incident field amplitude, E power. Now we need to find beta. The propagation constant. So this is the direction. So let me draw this here. So this is my direction. And this direction is my, because it is medium 1, I'm saying this as K1. Okay, it is K1. Now I want to decompose it. So I want to decompose it into these two. So see here, I'm just decomposing the propagation constant. So if this is my direction K1, then what will be this direction? This will be K1 times, what is this direction? Z. So it has a K1Z component, and this one has K1 times X component, right? If this is my direction, if this is my K bar dot, this is what? Instead of AS, let me just write, because we already got that R, which is this direction. So it has only X and Z. So that's why it is K1X times X plus K1Z times Z, right? Clear? So my direction of propagation, I'm now decomposing. This is my direction of propagation. So I'm erasing it because I need some space. So this was my direction of propagation, which was my K1 direction. I am decomposing it into K1Z XZ and K1X. Now, I want this K1Z and K1X. Sorry, guys, let me make it a little bit bigger because okay. So this is okay. So this is my K1 bar dot R bar, and this will have K1X time the component of K1 along Z. So it is K1Z times Z, and this is the component of K1 along X direction, K1X times X. So K1X times X, K1X times Z. Now, I want to now represent K1Z and K1X in terms of K1. Okay, so the magnitude K1 will be this one. So if I now replace this, so you can say that this is my magnitude K1. Now I want to replace represent K1X and K1Z in terms of K1. So how do I represent it? If you see here, this is my angle theta I, right? So therefore, this will be my angle theta I. So K1Z will be nothing but K1 cos theta I. See here, K1 cos theta I. And its the X component, which is K1X, will be K1 sine theta. Can you see here? K1 sine theta. So this is how I am getting my component of K1 along X direction and component of K1 along Z direction with the help of this argument. So this is my direction of propagation, arbitrary direction, and the propagation constant magnitude is K1. Okay, then this is its X component, this is its Z, this is its Z component, this is its X component. So the Z component will be K1 times cosine, and its X component will be K1 times sine, and this is X and this is Z. Got it? So this is for the incident. Now for the reflected, so for the reflected here, so for the reflected, again, this is my direction. Okay, and this is the component along the X direction. This is the component along the minus Z direction. So if this is my theta R, then this is my theta R. So if this is my K1, then this will be what? K1 sine theta R, and this will be K1 cos theta R. Got it? So if you see here, so it is reflected as ER0 e to the power of. So what is the direction? K1 sine theta I, sorry, K1 sine theta R times X, right? And then what is this direction? This is the negative direction. Can you see this? It's the negative direction. So that's why it is minus K1 cos theta minus K1 cos theta R times Z. And now if you see here, I am not changing anything here. The minus sign is as it is. The minus sign is as it is. Because The inside part is taking care of the direction. The inside part is taking care of the direction because it's an arbitrary direction. So this inside, so here the inside part, which is this one, is taking care of this direction. And the inside part, because one is positive and one is negative, then it is taking care of this direction. So that's why the minus is as it is. And for the transmitted, it will be the same because the transmitted will be very similar to my incident, except that the angle will be now theta t. So that's why if you see here, and here this is medium 1. So therefore you have K1, and here you have medium 2. So that's why you have K2, propagation constant K1 and K2. So that's why here you will have K2 sine theta t and K2 cos theta. Here we have K1 sine theta I and K1 cos theta I because we are in medium 1. Here K1 and the angle is theta I. That's why K1 sine theta I is K1 cos theta I. And here we are in this region, which is the transmitted region. So therefore we have K2 sine theta t because K2 and theta t, and here K2 cos theta. So this is how we can get our propagation constants. So the propagation constant for the incident, this is for the electric field, same thing will be for the magnetic field. Reflected, we got this. For the electric field, same thing will be for the transmitted field, and same thing for the magnetic field. And this one is for the transmitted field, and same thing is for the magnetic. Now, the last thing that we want is our magnetic field. So see here, magnetic field, because now if you see, this is my magnetic field, right? Now I will decompose it into 2. So this is 1 and this is 1. So this is an arbitrary direction. So this will be along a z direction and this will be along a x direction. So what part will be along ax direction? Yes, if this is theta I, then this will be theta I, right? This will be theta I. And can I say that this angle will be theta I? So therefore, you will have, yes, what will be the component of ax is EI0 over eta I. So what will be this component? It will be EI0 over eta 1 cos of theta I times minus ax e to the power of minus j this. So this will be the component. Can you see this? This will be the component. And what about this component? EI0 over eta 1 times, what will be this one? Sine. So it will be sine theta I. And what will be the direction? AZ times e power j. Got it? So this is my arbitrary direction. So I am getting its x component and z component. X component will be cosine theta. And it is minus because the direction is downwards. And my ax direction is upwards. So that's why it is minus cosine theta. And for my z, it is, the direction is the same. So it is only sine theta. Got it? So this is how you get the incident magnetic. I think, guys, we will stop here. In the next class, we will try to finish our perpendicular incidence, and then we will go to the parallel incidence. Okay? So thank you. We will meet on Thursday. If you have any questions, we will discuss it on Thursday. Okay?